Okay, good morning, everyone. Let's start. So can you hear me to the back? So I don't need to use the microphone. So yesterday we talked about the key technology trends for digital, for modern digital technologies. Basically, lots of the transistor counts per chip increases exponentially over the past 50 years, as described by Moore's law. And the key benefit is the reduction of the transistor cost and the cost per transistor. And Moore's law is still alive, but if someday the cost reduction trend is stopped, then Moore's law will be dead. So apart from the transistor count trend, there are other technology trends for modern digital circuits. The frequency of clock frequency of digital circuits has been increasing exponentially in the past. Also, it's roughly doubling every 2 years. But this turns flat. This trend turns flat in around the early in around 2003, 2004 for some reason. What the clock frequency is certainly closely coupled to the performance, to the speed of the applications. So the higher clock frequency, the faster applications that we can enjoy. Well, first, the CPU operates at 100 kilohertz, and now the clock frequency basically stay at 3 gigahertz or at the most 5 gigahertz. Probably it would increase a little bit, but not very much, due to a reason that is discussed in this slide. It's we know that power is closely related to the clock frequency. If we the power consumption of a digital chip contains two parts. One is I would say leakage power plus dynamic power. Leakage is static power. If the CPU is idle, it still consumes some power due to transistor current leakage. And this dynamic power has a famous equation. And this dynamic power is proportional to C VDD squared. C is capacitance. Basically, it's proportional to the size of the digital chip. VDD the supply voltage. We did the supply voltage squared, and F is clock frequency. Wow, so over the years, the supply voltage has been reduced, but clock frequency increases. But supply voltage has a little room for further reduction. It is now around 1 volt. Clock frequency, if we increase clock frequency, then this will certainly increase the dynamic power. In these two components, the second part dominates. Dynamic power is the useful power, the power used to perform some useful task. This is waste power. So the power consumption increases with the clock frequency and also the size. Actually, over the years, the chip size increases. But this trend has to be stopped. Otherwise, the digital chip will be too hot. The heat dissipation will be a huge problem. You could not remove the heat in time. Here is Intel's the power trend plotted by Intel. So this is power density in the y-axis and in log scale. So in early years, when we increase the power density, power per area, it's called power density. There's no problem. The heat can be removed by using natural air cooling or by using some fans. But in around this time, the power density increased to a level that can be compared to the power density in a nuclear power reactor. It's very hot. Imagine this clock frequency is several gigahertz, and the chip size is small, maybe 2 millimeter or 2 millimeter or 2 centimeter by 2 centimeter size. It generates a lot of heat. And if this trend is to be further extend, I mean, if we further increase clock frequency, then the power density would reach that in a rocket nozzle. And this is certainly not possible. It will be too hot. So at around that time, the clock frequency increasing trend has stopped. So the power has been kept at several gigahertz. So that's the power density trend. But we still want to have more speed from a digital chip. So nowadays, the speed comes from parallel processing. People put more cores in parallel to perform tasks at the same time. So speed is provided by more cores rather than increasing the clock frequency. Here we have a chart that put all those trends we discussed together. And this is Y scale. Y scale is a log scale without unit. Is a different unit for different curves. Horizontal is the year. The transistor counts increases roughly every 2 years, doubles every 2 years. This is in thousands. So here is 1 billion transistor in year 2010. And this curve extends until now. And this is performance provided by a state-of-the-art CPU increases. Clock frequency exponential increase firstly then saturates at around 5 gigahertz. And this is typical power consumption in watts. It saturates around 150 watts per chip. Here, this 100. This is 100 watts. So at this time, year 2005, when the clock frequency is more or less frozen, then we see another trend. The number of cores increases. So this is 10 10 cores, and typically in your smartphone there will be 16 cores, 16 CPU cores. So that's a new trend. So performance is provided by more parallel processing rather than increasing clock speed. That's a recent trend. Okay, any questions? So Moore's law is still alive and could be continued for maybe a decade or more, but eventually there will be end of the road. And here is a famous chart created by this organization, ITRS. It's an industry organization, industry alliance. It provides this technology roadmap. Along this downward direction is the continuation of the Moore's law. Basically, we want a transistor to be shrinked continuously. That's more so-called Moore. We want Moore's law to continue. The technology, transistor size, feature size shrinks from 130 nanometer to 90 nanometer, 65, 45, 32, 22. Now it's so-called 5 or 3. But we have some clarification on the newest technology later today. So basically, this is for digital circuits, digital technologies. We for CPUs, memories, logic circuits. We wanted a continuation of Moore's law. We want more digital content to be processed on a chip. The chip can be called a system on chip. It's no longer a circuit block. It's can be a complex system. Then, so this is CMOS scaling. CMOS transaction becomes smaller and smaller, but one day it will reach some limit, physical limit. But this has been said in the past. So even Moore himself mentioned that Moore's law will stop in early 2000. Year 2000, but it has been kept alive to today. And there is no replacement technology that we can see now. The main reason is the low cost provided by CMOS technology, the transistor per cost. The transistor cost, the cost per transistor is extremely small. I don't see any other technology that can replace CMOS in the near future. People are talking about quantum. It is a possible future technology, but not in the near future, not in the coming 20 years, maybe beyond 20 years. That's my personal opinion. Another trend on top of this continuation of Moore's law is diversification. As more than it's called more than more. Basically, it's more than digital circuits, more than digital contents. We want the digital chip to include non-digital contents. For example, to interface with analog signal and the radio frequency signal, so that it can interact with people and environment. We want to include some high voltage power devices. And this is no longer to process information. It's to manage power. To interact with sensors and actuators, or to interact with biochips. And these analog or other non-digital contents could be packaged on the same chip as the digital IC. So we can combine both these non-digital and digital contents on the same package. And here is a more and more technology example. This company, STMicroelectronics, is a leading company in providing power transistors. It provides a process called BCD, bipolar CMOS DMOS, for high voltage ICs. And high voltage ICs are important in applications like automotive market for the cars, or in the planes, or in some electrical network, power network, power grids. This STMicroelectronics provides these technologies. BCD technology are down to currently down to 0.11 micrometer, that's 110 nanometer. But the voltage can be very high, as 100 watt. Some denser technology is under development. 40 nanometer technology. Regarding the trend, this is the last slide about application. In the from 1970 to 1980s, mainframe scientific computing and data processing were the major applications of digital circuits. Then in 1990s, personal computers, internet become the major applications. And new millennium, smartphones applications becomes the main technology driver, the application that drives the technology development. And in the future, these applications could be the driving forces for technology development. They include healthcare, wellness, telemedicine, education, autonomous driving, gaming, entertainment, virtual reality, and augmented reality, visualization, and the cloud computing. Okay, so that's about the technology trends. Do you have any questions? If no, let's continue to the next topic, CMOS fabrication process. Well, CMOS is so important, so we need to have some understanding of how it is manufactured. So in order to understanding the manufacturing process, we take a look at the process to manufacture an inverter. Well, this is a symbol for inverter, the most basic building block for digital circuits. This is the transistor level circuit. So basically, it contains an N-channel MOS transistor, a P-channel transistor. They are connected in stack between the supply, between the supply and the ground. The gate side serves as the input, and the drain side is the output. So when the common gate and the gate are short together, when signal A is high, the NMOS will be turned on, PMOS turned off, so the output is connected to ground through a low resistance channel, low impedance channel to ground. So Y becomes low. When the input is low, I need to turn on the PMOS, turn off the NMOS. So Y is short to VDD and is regarded as 1. So here we have three representations of an inverter: a symbol representation, a choose table, and a schematic description of an inverter. Physically, the CMOS inverter looks like this. This is a cross-sectional diagram of a CMOS inverter. So this part of the device is NMOS, N-channel MOSFET. And this region is the gate. So we apply a high or low voltage to the gate to control whether or not the current can flow through this channel region. The gate voltage controls whether or not current flows through this channel from one of the diffusion region to the other diffusion region. For NMOS, we connect one of our diffusion region to the ground, and this is called a source terminal. The other is called a drain terminal. And for the PMOS, we need a P-type diffusion, a P-type diffusion here. And it is fabricated on a N region. So we need to create an N region called N wear on top of the substrate. And this is the gate. This gray area represents the oxide layer, the insulating layer. So for the PMOS, if we apply a low voltage to the gate area, and it attracts holes to this region, so a channel is established, so current can flow through it. So basically, this MOSFET in the digital circuit serves as switches. They are on-off switches. The control is provided to the gate terminal. So do you have any problem with this device structure? Yes.
What's the purpose of metal?
Purpose of metal, right? Is it okay? Thank you for your question. The metal is to connect this semiconductor region to the external world. We need to provide voltage, or to read the voltage from certain semiconductor region. So we need metal connection. It's just kind of wild. So here we have different regions. You see metals. And the gate is formed by a layer called polysilicon. It's kind of a highly conducting silicon layer. Diffusion region, N-type diffusion, P-type diffusion, and silicon dioxide. Well, actually, this is a more complete diagram for the inverter's device structure. We also need to access to the substrate and the N-wire. So we need to provide some contact to the P-type substrate. And this must be done through a region, a highly doped region. This P+, also called diffusion region, is connect to the substrate to provide electrical connection to the substrate. And this N-wire is connect to the metal through a heavily doped N+ region. N+ means heavily doped. So in the next 10 or 20 minutes, we are going to study how to form such a structure in a modern integrated circuit fabrication facility. And this, well, the transistors and those metal wires are defined by a set of masks, photo masks. So we need to have some geometry pattern for each layer, for the diffusion layer, for the metal layer, for polysilicon area. And this is the top view, which shows those masks. Say this green, this is top view that shows the metal the mask pattern. This is the green here. Here is the drain region of the MOS. This is source region of the MOS, and this orange is the substrate contact. This is the gate, polysilicon layer. For inverter, the gate of MOS and the gate of PMOS are connected together. So we just use one connected layer for the gate. And this blue rectangle represents the supply, the wire, wire to the supply, the ground. So we have different these rectangle shapes for if we just expand those masks, we see 6 layers or 6 masks for the not inverter. We have N-wire. This is N-wire region. We need to define a region, N-wire region with this shape and this size. Polysilicon, N+ diffusion, diffuse into the substrate. P+ diffusion, diffusion into the wire. Sorry, this is P+ diffusion into the substrate, and this is N+ diffusion into the N-wire contact and the N-wire the N-type transistors, source and drain. And this is to the PMOS source and drain, and then this contact to the semiconductor diffusion regions. And this metal layer. So from the structural point of view, transistors are just stacks of polysilicon gate, oxide, and silicon, and interconnects are stacks of metals. And this pattern of different layers are created on the silicon wafer with a critical process called photolithography. And on each step, different materials are deposited or etched. And these processes are carried out in a huge facility called fabs, IC fabs. And it contains clean rooms as large as football fields. So the critical process is the photolithography process, and we are go through this in some details. Let's omit the photo first. Lithography is such a thing. Lithog means stone, graph. This lithography is a process to transfer the pattern from stone to paper. So it uses inscribed stones, ink, and pressure to transfer pattern from stone to paper. Well, the transfer pattern can be positive image or negative image, like the film in the photo film in the past. It's a negative image. Or this is negative image. This is positive image. Now, in the photolithography, we replace the stone, or we can treat the stone as the masks, and this paper as a silicon wafer. But we don't use ink and pressure. We use so-called photoresist and the light. So this photolithography system is like this. So this is like a stone, inscribed stone. Lastly, photo mask. In short, is mask. It's basically some glass with pattern. Some region is transparent, some is not. So it's patterned glass. Transparent to light, certain light with certain wavelength. So lastly, like an inscribed stone, and this wafer is like paper, and the ink is like photoresist. So we expose this photoresist to some light. So the light source could be is usually ultraviolet or some shorter wavelength one. Ultraviolet light sources. As light source, it goes through the patterned glasses, and some region of the photoresist is exposed to the light, some are not. While in this example, it used negative photoresist, which means the region that is exposed to light becomes hardened, and the region that is not exposed to light can be removed by solvent later. So that's the basic idea of photolithography process. We transfer pattern from photomask into a photoresist. Then we apply some process steps Here shows the typical cycle for each process step. So for example, to create an the source or gate source and the diffusion region, source and drain region. For that step, we need to go through this manufacturing process. We needed to go through this cycle once. So a typical cycle starts with this oxidation. We grow an oxide over the entire wafer. Then we coat photoresist onto the entire wafer. This is like you put some ink there. And then we expose this wafer with a coated photoresist to light through a photo mask, through the mask. Then we develop the photoresist, so to remove those unexposed region. Then we apply SH to remove oxide layers not protected by the photoresist. Spin rings dry. So now we created some opening in the opening of the wafer. So on that region, open the region, we can apply process steps. For example, metal etch, metal deposition, a chemical vapor deposition to create a gate, or ion implant to create a source and drain region. So for each step, we need to go through this cycle one time. Then, so we go through this steps for the inverter structure we mentioned. So everything starts with a clean wafer, say 12-inch wafer, very pure crystal wafer, lightly doped, nice blank wafer. Then we're going to build the inverter from the bottom up, from the lowest layer to the topmost layer. So the first step will be to form the N-wear region. This is carried out through 4 steps. First, cover the wafer with silicon dioxide, protective layer. Then remove silicon dioxide where N-wear should be built. Then apply the manufacturing step here, either implant or diffuse, and dopants into the exposed wafer. And lastly, strip off the silicon dioxide, the oxide layer, the protective layer. Now let's go through it. So first is to form a protective oxide layer here for the entire wafer. This is oxidation process. This is performed by growing a layer on top of a silicon wafer in an oven, in a furnace with high temperature, using oxygen or water vapor. So this thin layer is growth. Then we deploy a photoresist layer, a spin on photoresist. So this is so this is photoresist is put on using this spinning process. And the photoresist is a material that is it's an organic polymer material that is light sensitive. When exposed to light, can become softened or hardened. There are 2 types of photomask, either positive or negative. It's like the stone printing can be negative or positive. So for the positive photoresist, the region that is exposed to light is softened and it can be removed by using solvent. So next is to expose the wafer to light through a mask. This is a layer of a mask. It's the N-wear mask. So this region of photoresist is exposed to light. It becomes softened and it can be removed, can be stripped off by using a solvent. Okay, so photoresist is removed. Next is to remove this oxide layer, protective oxide layer under the photoresist. So this is done by the etching process. So we etch away oxide with hydrofluoric acid. And this is a nasty stuff. It's toxic. So the silicon dioxide that is covered by photoresist won't be etched away. Only this part is etched away. And then we spin, rinse, and dry. So to remove this photoresist. So only this protective oxide region is here. We need the oxide layer rather than the photoresist because photoresist will melt in high temperature in the next step, but silicon dioxide won't. Okay, so with this silicon dioxide layer protecting the substrate here, now we have an opening region here, and we can apply the semiconductor step here. So to form the N-wear, so N-wear can be formed through diffusion or ion implantation, two different alternative approaches. Diffusion is to place the wafer in furnace with arsenic gas. Arsenic is column-5 element. So those column-5 atoms can diffuse into this region. So this part of semiconductor becomes N-type, N-wear. So diffuse, we need to heat it. Another approach is ion implantation, just to blast wafer like a bullet. Blast wafer with beams of arsenic ions. So only this part of substrate will be implanted, become N-type region. Others remain protected. And last, for this N-wear formation is to strip off this protective oxide layer. Now N-wear is formed. You see, even for a simple process like forming an N-wear, it involves a lot of steps. We need an oxide layer and then photoresist. Because there is high temperature, the photoresist will melt under high temperature. Instead we need a silicon dioxide layer to be the protective region in the process. Okay, so that's basically now we have go through one cycle for one manufacturing step to form the N-wear. So every other step is similar, and we need to go through this cycle one time. Now let's take a break, 5 minutes break. Okay, let's resume the lecture. So for the tutorial, today we won't have tutorial. It starts next week. Okay, so now we learn how the first layer, the lowest layer is formed, the NVIDIA, how NVIDIA region is formed. Let's go through the process for the other regions. Next one is for the gate, a polysilicon gate. This gate layer is formed by deposed a polysilicon. So first we grow a thin layer, thin gate oxide layer over the entire wafer. Then we deposit through a process called chemical vapor deposition. So this process can deposit polysilicon on top or on the entire wafer. And this is even layer. This is an even layer, not patterned yet. And this gate layer is heavily doped to provide high conductivity. Now to pattern this polysilicon gate layer, we'll go through last cycle once again. So just go through that entire cycle. So basically, on top of this polysilicon, we grow a silicon dioxide, then deposit the photoresist, then expose to the light, then remove the exposed photoresist region, then etch the silicon dioxide layer, then further etch down. So the entire process. So we etched away those region that we don't want polysilicon. This is the top view. Then after this process, silicon dioxide, polysilicon region is formed for the gate. And some of you may argue that why we don't form the diffusion region first, the drain and source region first. I said before that we create regions from bottom up. The drain source region are below the gate region. The reason for this is that this polysilicon gate region can serve as a protective region, protective layer for the implantation process, and it is it just serves as a protective region, and it leads to a process called self-aligned process. It is simplified the manufacturing process that I will describe later. But anyway, here we form polysilicon next to the N-type region, N-ware region. The second step here. Okay, then next step is to create the diffusion region. N-type diffusion and P-type diffusion. Let's consider this self-aligned process. Let me explain it in details later. So let's consider the N diffusion region. The N diffusion is like this. We have N here for the MOS, for the drain and source of the MOS. And we also need to have the contact to the N-ware here. So this is N-ware region, not N-ware, the N diffusion region. And the thing here is that we do on this is top view. We do not pattern this drain and source like this. We can do that in this way. This is N plus region. This is another N plus region, but that requires a very careful alignment to the edge of the this gate. And this alignment can be very difficult, very challenging. And through this, through forming the polysilicon layer first, people can solve a lot of problems very cleverly. So instead of two separate N regions, we use this single N plus mask that covers this gate region. Now, so in the formation of the diffusion like this, so now to form the N region, this region is opened, not covered by silicon dioxide. This silicon dioxide is protective region. This region is also not open and not covered by silicon dioxide. But this region here is protected by the gate material, the polysilicon gate. This polysilicon gate can also serve as a blocking layer for the implantation. And so this is opened. Okay, so here, although we have one single region here, actually we have two separate openings. It is self-aligned, automatically aligned to the gate. So this is called self-alignment process. We form polysilicon first before forming the diffusion. Then we apply the implantation. Typically, implantation process is applied. So we blast the ions, the respective ions, into this region. Blast. So those so arsenic ions implant like bullets, inject to those regions, and this part is automatically blocked by the gate. Therefore, here we don't have N region formed. Modern day use implantation for the formation of the diffusion regions. However, due to historical region, these regions are still called diffusion regions. Diffusion is a process, like a formation of N-ware. We diffuse the ions into the wafer. That's a historical way, but today we still call this source and drain region as diffusion region, but it is realized by implantation. And this diffusion region for the N-ware contact. So this is third step to form the diffusion region, N-type diffusion region. Then we will remove the silicon dioxide, remove this this cuff and this protective silicon dioxide layer. So after these three processes, we get N-ware formed, polysilicon gate formed, and N-type diffusion layer formed. The fourth step is to form the P-type diffusion, similar to N-type diffusion. So here, in this region, we need a P-plus connection to substrate. And here we need P-plus for the drain and source of the P transistor. Again, a single rectangle rather than two separate ones is used because this gate can serve as the blocking layer under the channel. So this channel region won't become P-plus. So this is the fourth step. The next step is to form contacts again, the whole entire cycle needs to be gone through. So deposit, to grow a silicon dioxide layer over the entire wafer, then deposit then spin the photoresist, expose to the light, then develop the photoresist, and remove the unexposed photoresist, and etch this oxide layer, so etch the oxide layer, then apply the process of metal, creating metal contacts. So these metal contacts are created. So next is to deposit metal. Metal can be deposited into the wafer over the whole wafer. So basically, we have a mask. So these regions will be so we depose metals to these regions defined by the metal mask. And because we have opening here, so this metal can be filling these gaps. So it provides contact to the semiconductor regions. Well, so that's the whole 6 steps in this simple inverter. This is first metal. And in actual IC, we have many layers of metals to provide connections. Well, for the metal, copper is the dominant type of material in modern technologies. In the past, has been aluminum. Aluminum is one is easier to form, but copper has a higher performance in terms of conductivity. And let me see. Here is a video showing the chip structure. Let's take a look at this. No sound. Let's take a look. This is a packaged IC. Most wires, I see the bonding wires. Then zoom into the chip itself. These bonding wires, connection to the chip from outside world. Use scanning electron microscope to view the chip. So these are metal wires. Many layers of metal wires. Okay. So basically we can see metal wires in this video. Transistor are beneath the wires, and the wires have different width and thickness for different layers. Turn on the Zoom. Okay. Share this. Okay. The metal stacks are like this. The bottom layer, this is bottom layer. This is wafer transistors are here in the semiconductor region. The bottom metal layers have the pitch. So pitch means width and spacing. The sizes are matched to the transistor size, very small. And intermediate metal layers are 2 to 4 times wider than the bottom layer metals. And top layers are wide and thick. You see, these are to provide low resistivity connections for long wires like power supply wires and clock wires. Okay, so that's a brief overview of the manufacturing process in a digital IC technology. Do you have any questions regarding the process? If no, let's continue. The process I described is a classical process. It's not the latest technology. Latest technology are more complex. So we want to make a transistor smaller and smaller. So the pattern we need to define on the silicon is very fine, very small. And the technology we use to define a pattern is this photolithography technology. Basically, we need a light source to project image on mask onto photoresist. And there is a resolution limit there. So for any imaging system, optical imaging system, there is a resolution limit. And this resolution limit is determined by the famous Rayleigh's equation, right? So called diffraction limit. Well, this is something that you could learn in depth in an optical course in EE, but we are not going to go. We are not going to dig into that. Here, I just use the result. The resolution, which means minimum resolvable feature in the photolithography process, is proportional to the wavelength lambda of the light source. That's key parameter, lambda. There is also other parameters, including this NA, so-called numerical aperture of the projecting system. Basically, numerical aperture is related to the angle of the light cone. So for example here, this light numerical aperture has a value of 0.12. When the angle here is 7 degrees. This light cone angle, half angle, we say half angle is 7 degrees. The numerical aperture is 0.12. And for this one, the cone, this is light cone, angle is 60 degrees. The numerical aperture is 0.87. Basically, this NA is smaller than 1. The best you can get is 1. So that's the resolution. And also K1, a parameter K1. K1 is a constant that depends on the specific photoresist material, process technology, and some other things. So that's the resolution limit. But the projecting system is a 3D, not only 2D, because the focus, line of focus here, the focus has a depth, a certain depth. And this depth of focus, that DOF, depth of focus, is also proportional to the wavelength. You get a smaller wavelength, it gets worse. For resolution R, we want it to be small, R to be small. But the depth of focus, small is difficult, small is challenging because we need to align the wafer very precisely. A small deviation from the supposed position will cause some error. And this DOF is inversely proportional to the numerical aperture squared. So when you reduce, increase the NA, numerical aperture, you improve the resolution, you make it R smaller. But at the same time, you make the focus of depth even smaller because of square there. So the depth of focus becomes smaller. This is not good. So contradicting. But anyway, from this paper, Nature 2000 paper, we can draw a conclusion that the practical resolution limit is around half the wavelength, lambda over 2. Of course, this depends on many things. Depending on K1, depending on numerical aperture, also depends on some correction techniques. But this is in a classical photolithography system. The resolution is limited to half the wavelength of the exposure light. This is half length, and the light source is not easy to obtain. There are some, so we use lasers, different kind of laser technologies to generate the light source. So these are the laser technologies and the corresponding wavelengths of the laser light. So this one is the current popular one. It has a wavelength of 193 nanometer, close to 200. This is the dominant technology, laser technology, right? Today. So if the resolution is about what? Let me show you this slide. So the refinement of a transistor's size has been enabled by the advancement of photolithography technology. For the light source, currently we use many foundries use 193 nanometer light source called deep ultraviolet light source. I think you have heard of this a lot from the news. And from the previous paper, so the resolution is about half the wavelength. So it's around, say, 90 nanometer. But with some tricks, people well, but actually, people are able to use deep ultraviolet light source for technologies below the conventional limit. They can apply this deep UV technology into 45 nanometer, 32, 22 nanometer technology using this kind of so-called resolution enhancement techniques. But next generation, or the newest generation of photolithography light source is the extreme ultraviolet system, EUV. In this chart, this blue curve represents the nominal feature size scaling. And this is light source. You see, the light source doesn't go down as fast as the nominal feature size, but people can still manage to advance in the transistor size because of some very sophisticated and smart techniques. So deep UV photolithography system means wavelength of 139 nanometer. The conventional resolution is well, I say half wavelength, but still in the conventional system, 65 nanometer is possible. So the deep UV is possible for 65 nanometer or above. When the air is the medium, suppose the largest numerical aperture of 1 is used. That's the limit, conventional limit. But manufacturers have extended this 193 nanometer technology to produce future sizes significantly below the conventional limit. 45, 32, 22 nanometer down to so-called 7 nanometer technology. Can also use this deep UV technology. This is made possible by the invention of a number of resolution enhancement techniques, including the following: optical proximity correction, phase shift, immersion lithography, multi-patterning technologies, or a combination of them can be used. So, I briefly introduce these techniques. The first one is optical proximity correction, OPC. So in an optical lithography system, there are many error sources. So we wanted to transfer the pattern on the mask into the photoresist. That's our purpose. But this pattern transfer could be corrupt by many errors in the optical system. And these error sources include illumination non-uniformity, optical aberration, optical diffraction, and lens geometry distortion. We cannot make a perfect lens. Interference between features and nonlinear photoresist response to the light. non-planar resist surface. Surface is not it's many error sources. So this will lead to a pattern transfer error. And this optical proximity correction can compensate these errors by modifying the mask patterns. Basically, the presence or absence of neighboring features will affect the width and spacing of the features. So some algorithms were invented to apply this neighboring effect to correct the pattern transfer error. And here is a illustration of this OPC technique. So the blue one, the blue rectangle, blue shape pattern is the desirable pattern that we want to create on the photoresist. This is the one drawn by the physical designer, by IC designer, and by the layout designer. And then the green one is the actual mask pattern used in the manufacturing process. You see, it's very different from the intended one, intended blue one. The green one is while the manufacturer applies some algorithm to generate this green pattern. And in the actual manufacturing, the red shape of photoresist is formed. The actual one is very close to the intended one. But only after applying this OPC algorithm, only after using this complicated and strange shapes. So here illustrates two different approaches. Say if we use the layout directly in those say sub 90 nanometer technology, the created pattern will be highly deviate from the desired pattern. So this is a desired pattern, but if you just use this pattern for the mask, you get some shape like this. Especially for when the diffraction limit is there. Now the manufacturer uses this kind of mask, apply OPC techniques. Then after the exposure to the light, this pattern is developed, which is very close to the desired one. So this is first technique, OPC, for deep UV technology for resolutions at 65 nanometer or below. Actually, even from 90 nanometer technology, this OPC technique has been applied. The second technique is phase shift masks. This is the mask with this phase shift technique. It's just a glass is a mask is just a glass layer, either transparent or not transparent. The phase shift mask is a thing that have different depths for the same, say, transparent layer. And we know that the light have different wavelengths in different mediums. The light has, say, shorter wavelengths in the glass, and in the air is longer wavelengths. So So in here we have a thinner layer, thinner mask, a little thicker mask, and this will create phase difference in the light. And somehow people can utilize this phase shift techniques to enhance the contrast of the pattern on the photoresist, enhance the edge contrast in the image on the photoresist, and remove some of the sub-wavelength effects. The third technology is a trick, very, I would say, very simple, very clever. It's called immersion lithography. Idea is very simple. It's to inject pure water in the processing system. So between the length and the wafer, we fill it with high quality pure water. The water has a refraction index of 1.44. This effectively decreases the wavelength by the same factor. And so this effectively increases the resolution. So our idea is very simple, but in the actual implementation, I believe there are many challenges to be overcome. And the next one that I go through is called multi-patterning. Say, if using DUV technology, we cannot pattern where some small feature, some small feature sizes, but we can do this patterning twice. So we split this layer into two patterns. So we say, let's say this is 1, 2, 3, 4, 5 lines. We put 1, 3, 5 on one mask, and 2 and 4 lines on the other mask. And we expose it twice, perform this photolithography twice. And it can somehow, they can, those manufacturers can manage to use this double patterning techniques to refine the resolution. This reduces optical interference effects. And it can even, well, in 7 nanometer process, quadruple patterning is used. So one regular mask is split into 4 different mask set, 4 different masks. But there are challenges because you split 1 into 2, then you need to align these 2 different masks precisely. You need to align, say, this one sets here. This one will be aligned to this one. This aligning in different manufacturing step is challenging. But in the modern precision machining, the manufacturers, they can do that. And there are many other resolution enhancement techniques. So with those very clever engineering techniques, the deep UV technologies has been able to apply to 7 nanometer process, down to 7 nanometer technologies. It's far beyond the diffraction limit, the optical diffraction limit. Optical diffraction limit is half the wavelength, 90 nanometer, but now it's far below that. Well, I think we still have a couple of minutes. Let's go through this last 2 slides for today. The DUV is can manage down to 7 nanometer fabrication. The newer generation has to rely on shorter wavelength light source. It is the so-called EUV system, extreme ultraviolet lithography system. It refers to a light wavelength of 11 nanometer to 13 nanometer. And there are good light sources that can generate this EUV. So with, well, even with those in the DUV we just mentioned, 190 nanometer light source. Even with those RET, resolution enhancement techniques, there are still a lot of there are a lot of design restrictions in the layout. It imposes a lot of restrictions in the layout. And in the deep UV, in the EUV, this if EUV can be applied, then many of the restrictions in the DUV technology can be removed. So, and this EUV technology is necessary for 5 nanometer or below. But EUV is not an easy thing. There are many challenges. The first thing is that an all reflective optical system must be used. It cannot use lens. Lens has a high absorption rate for EUV light. So mirrors must be used instead of lens. Mirrors must be used. And the system is like this: mirror system, light source, EUV light source, a lot of mirrors. This is for the mask, and finally defined to the wafer. And many mirrors, like this mirror, is not a flat mirror; it's curved. And it's not only curved; it's a spherical, not like a perfect sphere. And well, you need multi-layer structures, not rely on interference effects to achieve reflectivity. Like there's many layers of mirrors, and it needs to be extremely precise. The geometry errors and the surface roughness less than 0.1 to 0.2 nanometer. You know, it's 0.1 nanometer, a tenth of nanometer. The thickness error, the geometry error, that's very highly precise. So hence, it needs an extremely high resolution metrology system to measure it, position it. So far, the only company, only manufacturer that can make an EUV lithography system is one, maybe you know it. Do you know which company is it? It's called ASML, located in Netherlands. That's the only company. But it has this ASML has some connection to a Hong Kong company called ASM. ASM is a listed company in Hong Kong stock market. Many of our students went to that company for work study, or they work there after graduation. So these two companies, so that ASM has some connection to ASML, the Netherlands company has some connection to a Hong Kong company called ASM. And lastly, laser source is also a challenge for EUV. It's not simple to create an EUV light source here. Okay, that's all for today. Do you have any questions? I know, so see you next week.